Okay, so this is our goal for today. We're going to talk about the force exerted on a current carrying wire. And it's not a coincidence that this looks like QVB sine theta. So if you think about what a current is, it's a whole bunch of flowing charges. And so if a magnetic field can exert a force on a single moving charge, when you have a whole collection of moving charges in the form of a current, then you get a nice force on those guys. And you can write that in a very similar equation to QVB sine theta. It's totally equivalent to QVB sine theta. It's ILB sine theta. And there's a right-hand rule, and it works the same way that the right-hand rule works for the force on a moving charge. But one nice thing is you never have to worry about your right hand lying to you in this version of it, because the direction of current is defined to be the direction of flow of positive charges. Okay? So when you do the QVB rule, you just have fingers in the direction of the current, curl them into the magnetic field direction. Your thumb, for sure, points in the direction of the force experienced by that current. You don't have to worry about flipping it, because we're talking about positive charges flowing here. That's our definition of which way current is. Okay, so we're going to get to that point, but we're a little bit ahead of ourselves. So we're just going to pick up, for now, from where we left off the other day. Okay, so we did this example of the velocity selector, the second stage of our mass spectrometer. And so our velocity selector had two fields in it. We have a parallel plate capacitor here, positive plate, negative plate, a wonderful uniform electric field in there. And in this case, we have a positive charge passing through. And so the electric force, the force exerted by the electric field on that positive charge, is directed down. That's the purple arrow. And then we set up a magnetic field, which is in the appropriate direction to produce this force that is exactly balancing the electric force. And we figured out what direction that magnetic field had to be to make this happen. Okay, so now we're going to, instead of firing positive charges through our velocity selector, we're going to fire negative charges through. And we want them to pass through undeflected. Okay, so if we have negative charges going through the velocity selector instead, what, if anything, do we need to change about the velocity selector? Okay, so that's our first question today. So change the charge sign from positive to negative. What corresponding change or changes or none do you have to make the velocity selector function? Okay, so we're all over the place here. So we've got more votes for 2 than anything else. So one thing to think about is, think about this free body diagram, right? So this, remember, was stage 2 of our mass spectrometer. And stage 3 is separating out the particles based solely on mass. And we don't want to have them separate out based on mass and different speeds. So we've got to make sure all the particles arriving at that separation stage have the same speed. So this device makes sure that happens. Okay? So these forces only balance on this positive charge if it's going just the right speed. Remember, the magnetic force is speed dependent. So if we fire particles that are going faster than this through the velocity selector, the magnetic force is larger. The electric force stays the same. And that particle bends up out of the beam, and we get rid of it. And if it goes slower than this particle, then the magnetic force goes down, because, again, the magnetic force is proportional to the speed. And that force would bend down out of the beam, because the electric force would be larger than the magnetic force in that case. And only if you're going just the right speed, as this particle is, do you go straight through undeflected. Okay? So what would change about the free body diagram if we flipped the sign of this charge to a negative? Would we see any change on the free body diagram? Yes? So the electric, yes. So wouldn't the electric force be in the other direction? Okay, so we've still got positive plate here, negative plate here. We've got this lovely field directed down, but we flip the sign of the charge to negative. And of course, F is QE. And so if you've got a negative charge on your particle, you feel an electric force which is opposite to the direction of the electric field. So that FE force would point up. Are we okay with that? Okay. So the electric force reverses direction. All right. And if we didn't want it to reverse direction, we would have to, say, reverse the direction of the electric field. Okay. But do we have to do that or not? So what would happen to the magnetic force? So what determines the direction of the magnetic force? You get your right-hand rule and you figure that out, right? So your right hand tells you which way the force goes. So we should figure out again which way the field is in this case, the electric field, that is. Sorry, we know the electric field, the magnetic field. So our fingers are the velocity of the particle, the magnetic force is the thumb, and so you curl your fingers into the magnetic field. So the magnetic field is directed into the screen in this picture. And that's what gives rise to that magnetic force directed up. Okay, so if we do not change the direction of the magnetic field and we flip the sign of the charge from positive to negative, does anything happen to the force direction? It switches directions too. It goes in the exact opposite direction. Okay, so the electric force flips over, so it's directed up, and the magnetic force flips over, so it's directed down. Okay. So what's that particle going to do? Is it going to pass through undeflected, which is our goal? If it's going just the right speed, pass through undeflected, we're fine. Okay? So we don't actually need to change anything. It works just fine the way it is because both those forces flip direction. Okay, so let's see it again. So there's the positive. And the negative looks very similar. You've got to really look close to see the difference, actually. And the only difference is the blue arrow is going down here where it was going up before, and the purple arrow was going the opposite direction on the two pictures. But in both cases, the force is balanced, and we're fine. One thing that would be different is faster particles the first time would bend up out of the beam. And in the second case, if they're faster than the magical v equals e over b speed, those particles would bend down out of the beam. But we still get rid of them, so we're perfectly fine. Okay, any questions about velocity selector? Okay, so then we've got this crazy thing called a cyclotron. So this is a particle accelerator, and the first one, Ernest Lawrence actually won a Nobel Prize for this, for making this thing. And the first one was small enough that Ernest Lawrence could fit it inside his shirt pocket. Okay? So it's a particle accelerator, and normally you think of particle accelerators as these massive labs in Switzerland buried under the ground, 28 kilometers around in a circle. It's hard to fit that in your pocket, but this is one you can actually fit in your pocket. And it uses, again, the forces that are exerted by electric and magnetic fields on charged particles. So it's a nice thing for us to consider. And you can see these two blue regions. They're D-shaped, and so we're very inventive as physicists, and we call them Ds. Okay, so there's a right D and there's a left D. Okay, and in the gap between the Ds, there is an electric field. And in the Ds themselves, there are magnetic fields, one in the left D and one in the right D. And so the particle exposed to the magnetic field will spin around following a circular path. And in the gap, you've got an electric field there, and so you just have an acceleration across the gap. So here's our cyclotron in action. Okay? So we start off with the particle at rest right here. We let it go from rest. But there's an electric field that makes it accelerate across the gap. Then the magnetic field bends it, comes back across the gap, et cetera, et cetera. Every time it crosses the gap, it's getting faster. Remember, the magnetic field cannot change the speed. All it can do is change the direction. So the role of the magnetic field is simply to bring it back to the gap so it can get another boost in energy. Every time it crosses that gap, it gets another energy boost. Okay, so by the time it's done, it gets spit out of this thing going pretty fast. So think about how this works a little bit. Let me ask you some questions about it, just from here. So we let it go from here. Let's say it's a positive charge. Okay, it's a positive charge, and you see it accelerate to the right across the gap. Okay, it started from rest. Now it's not at rest. Well, it's at rest now because I paused it. But anyway, which way is the electric field in this gap? To the right. Okay, because the force on it is clearly to the right. It's a positive charge. F equals QE. Okay. Keep going. Now we have a magnetic field acting on it. Spins it around in a circle. Remember, there's a radius here, and we derived the equation for the radius, mv over qb. And so we have a relatively small speed at this point, so we have a relatively small radius. And as the speed gets bigger, the radius correspondingly gets bigger too. That's mv over qb doing this. Okay. So then it crosses the gap again, and maybe I'll do this version of it. I'll show the energy every time. So the first time across the gap, the kinetic energy went up by 20 energy units. And the next time it crossed the gap, the energy goes up by 20 energy units. And every time it crosses the gap, the energy will go up by 20 energy units. Okay. The second time it crossed the gap, which way is the electric field? To the left. So the first time was to the right. The next time was to the left. Okay? So every time it crosses the gap, you have to be clever enough to reverse the field direction. Okay? This sounds actually a lot harder than it really is. Because think about how much time it spends in the D. Okay? So we did something about how if you throw particles at different speeds into a magnetic field, they certainly go in paths of different radii. But what about the time? Time to go through a full circle, or in this case, what's relevant is time to go half a circle. How do those times compare? As the speed goes up, the radius of the path gets bigger. What about the time to go through that each half a circle in the D? It stays the same. So we derived this before. We derived an equation that says the time is actually independent of the speed. Okay? So you know how much time you have to work with. So in fact, all you need to do is not hook the two sides of the D's up to a battery, which would keep the voltage constant, potential difference constant across the gap, and the field the same direction. All you do is you hook it up to an alternating voltage, which you can get out of the wall socket, for instance. Okay? Now normally you need a little bit higher frequency you can get out of a wall socket, but all you need to do is hook it up to a source of alternating voltage, and that, if your frequency is just right, will give the electric field direction switch that you need. Okay? So it's not as hard as it sounds to keep the field going the right direction to give this a kick in energy of that it gets. Okay? So every time across it gets 20 energy units. Oh, and this is relevant to us. Certainly Ernest Lawrence did this way back. Back in 1939 he won the Nobel Prize, so the work he did was earlier than this. But you can just go down the river a couple of miles to MGH, and they have a really neat proton therapy center. Okay, there aren't too many of these things in the world, and we have one here in Boston at MGH. And so what you've got is an accelerator, and this is a picture I just grabbed off the web from MGH, the MGH site. Notice this is 40 feet here. Okay, that gives you some sense of the scale. So this is a massive, massive installation down at MGH. But you get the accelerator here. This is just basically a cyclotron. And you accelerate the particles around here, and you kick them out here. And then they don't travel in a straight line. In fact, they follow these sort of roughly circular paths here. So these blue things are what makes them travel in a circle. So what are those blue things? They're magnets. By adjusting the strength of this magnetic field produced by this magnet, you can make that particle bend in just the radius you need it to. And then you send the beam either here or straight. Okay, that's a piece of cake to do. You want it to go straight? Turn the magnet off. You want it to bend? Turn the magnet on. Then it knows to go this way. Similarly, you can make it go out here or bend in here. Okay, and then the patient is lying here and being hit by a beam of high energy protons, which go in there and mess up some cancer cells and things like that. Kill the tumors that are in the brain. We're just going back to analyze the cyclotron, though. And what I want to know is, in what direction is the magnetic field in the Ds? And we saw a positive charge. You saw which way, you can still see which way it's orbiting around. So what direction is the magnetic field in the Ds? Go for it. Okay. So that's interesting. Lots of votes for lots of things. Okay. So how do we answer this? How do we think about this? Do it? The right-hand rule. Yes, so we have to go through the right-hand rule to figure out what the answer is here. Now, there's one clue here that you can use to tell you, just by looking at the picture, whether the field is the same direction in the two Ds or in opposite directions in the two Ds. Okay? So who's got insight into that question? Same direction in both Ds or opposite directions in the two Ds? What gives it away? You say it's the same because? Did we get a good reason for either the same or opposite? What do you notice about the picture? What's going on? Yeah?
It's going in a circle.
It's uniform circular motion. And clockwise or counterclockwise? Counterclockwise in which D? In both Ds. That's it. Okay? So the circulation is counterclockwise in both. So you can imagine basically taking out the gap and then putting the things together, and they would just spin in circles. And that's what it would do in a uniform magnetic field, where you certainly weren't changing the direction from one side to the other. Okay? So the fact that you see spin counterclockwise, circulation counterclockwise on both sides, tells you, in fact, the magnetic field has to be the same on both sides. So now we're left with either 1 or 2 as our answer. Okay? I think we had more votes. So for 1 or 2, we had more votes for 2 than 1. Of course, we had a lot of votes for everything else, too. But that's OK. So then you get your right hand going. Okay? So let's say you pick some point. Let's just analyze the right D. Okay? And what I'm going to do is go to the very first time across. It comes into the D. It goes up. It's heading to the left. Just as it leaves the D into the gap, it's going to the left. Okay? So that's where I'm looking at it. Heading left across the gap, just leaving the right-hand D. So then I know my fingers point to the left, some way. I don't know quite how to orient my hand yet, but I'll get there. So my fingers are going to the left. Are we OK with that? And of course, you can pick different places on the path and do this, but I'm going to pick that point at the top of one of these circles. OK, so how do I know how to stop rotating my hand? How do I know where my hand is in the right direction? What else do I have to go on? I'm looking for what? Field. So you got to know the two other things, right? We know the velocity is going to the left. What's the third thing? Force. Do you know which way the force goes? It's circular motion, so force is always into the center of the circle. Bingo. Okay? So if you're at the top of the circle, which way is the center of the circle? That's below you, right? Okay, so you really want to have your hand like this. Are we OK with that? OK, and then you curl your fingers, and you'll get your field direction, as long as it's a positive charge, which it is in this case. So we're all set. So you curl your fingers, and they point into the screen. OK, so into the screen looks good for the right D. So questions on that? OK. Now, do we have to do a whole different thing to worry about the left-hand D? What we can do is actually we can just go across the gap to the point where it enters the left-hand D, and it's exactly the same, right? The velocity where it first enters the left-hand D is this way. The force is in the direction of the center of the circle, which again is down. So it's the same right-hand rule over there too. Okay? So got to be the same on either side. So let me move on to this. Force on a current carrying wire. And so magnetic field can certainly exert a force. And as I said before, if you can get a force on a moving charge from a magnetic field, you can certainly get one on a current, because what is it? It's a whole collection of moving charges. Okay, so that's fine. And so we go back to this. This is our force on a single moving charge equation. F equals qvb sine theta. And then you say, okay, what is charge? And this is something that's nice to remember for tonight. For instance, charge is current multiplied by time. And that's relevant for, say, charging capacitors and stuff like that even. And so you can replace Q in our equation by I times T. So then you get I V T B sine theta. Well, that's just too many variables to keep track of, right? So what do we notice there? We can combine, say, velocity times time. Velocity times time is, what kind of thing is it? It's a distance, okay? So we could just replace the velocity times time by length. And in fact, the relevant length is the length of the wire, in fact, that's in the field. And so we write our equation, which is completely equivalent to QVB sine theta, as ILB sine theta. So if you have a single charge moving in a magnetic field, use QVB sine theta. If you have a current in a magnetic field, then generally we use ILB sine theta. It's really completely the same thing. Okay, you can actually interchange. You can use the Q one all the time if you really want to. But this ILB sine theta version is handy to use for currents. Okay, so I is the current, L is the length of the wire, B is the magnetic field, and then you get sine theta, and theta represents the angle between something and something else. So what do you got? The angle between what and what? Between what and what? Between the current direction and the direction of the magnetic field. Exactly right. So that's what that theta represents. Okay, and again, you get your right-hand rule. So instead of V, now you get your fingers being I, the current direction, and everything else is the same. And like I said before, you never have to worry about your right-hand lying to you, because current, by definition, is positive charge flow, that direction. Okay, so do we believe this? Do we believe that magnetic fields can exert forces on currents? Well, let's see if we can see any evidence of that. Okay, so I have a power supply. This is called a DC power supply, direct current power supply. It's just like a fancy battery that I can change the voltage of, because I got this voltage knob on the front. Okay? And what it's connected to is there's a wire that goes from the positive terminal back to the negative terminal. This is actually not usually recommended. If you did this with a battery, you would be shorting out your battery. Okay? So you'd drain your battery in very short order if you do that. So we can get away with this one with the power supply for a little bit. If you notice it's smoking, let me know. Okay? So, and you'll notice that the wire happens to pass through this magnet. Okay? It goes right through almost the middle of where the magnetic field is from this magnet. And this magnet has a red part closer to you guys, and it's marked with an N, and then it's got a blue piece of tape that's marked with an S, and those N's and S's stand for north and south poles. And which way does the field go? Knowing where N is and where S is, which way does the magnetic field go? So the N is closer to you, the S is closer to the screen, closer to me. Which way is the magnetic field going? It's either going away from you or toward you. Any idea which way it's going? Does it come out of the North Pole, head to the South Pole, or vice versa? It does one of those things. Who remembers which way it goes? Let's take a vote. Okay? Who thinks it goes toward the screen, from the North Pole to the South Pole? Votes? Okay, several votes for that. Who thinks it goes the other way? A couple votes for that. Okay, so democracy rules, eh? How about that? We'll just say majority wins, which is correct in this case. So really does come out of the North Pole and to the South Pole. And of course, unlike electric field lines, which would stop when after they left a positive charge, ended on a negative charge, these guys, outside the magnet, the field lines go north to south. And then inside the magnet, the field lines wrap around and come back out. They go south to north inside the magnet itself. Okay, so they're complete loops. But the critical part is there's a field going this way. Our current comes out of the positive terminal. It's going to go this direction through our magnetic field, which we've decided is going in this direction. So the field is going toward the screen. The current is going this way through our magnetic field, that direction. Okay, so grab your right hands and tell me, predict for me, the direction of the force on that wire. Your right hands will tell you that. So fingers are current, curl them into the field direction. Your thumb will tell you, will predict for you which way the force is. What do you got? Straight up. Okay. Who agrees with that? Straight up? Disagree? Everybody get down? Okay. So it's sitting on a little piece of styrofoam. If it forces down, we're not going to see very much. So I hope it is up, because then it'll actually, we'll see if we can see any evidence of it going up. Okay, so we're looking for evidence of force on this wire, which is directed up. Okay, ready? So I'll turn on the power supply. And there's no voltage initially, so there's no current initially. So it's not surprising nothing's happening so far. So then I'll crank up the voltage, and I'll either blow the fuse or something will happen over here, and I'm not sure which will happen first. So we'll try and see. Oop. Anybody see any evidence of anything? What did you see? Anything? It actually hopped right out of the magnet. Okay, so put it back in again, crank up the voltage. Whoop. Okay, it doesn't want to be in there at all. It just hops right out. Okay, it starts in there, it goes, woo. We'll do it in slow motion, right? Here's a slow motion replay. Turn on the thing, goes up and over like that. Is that evidence of your force going up? I think so. I think so, right. And if I flip the thing over, so the current is now going this direction, then the field's still going this way, the current's now going that way, which way is the force going to be? It's going to go down, right? Okay, so now, if it really works right, it shouldn't pop out, right? So let's see. Let's see. Turn this, there we go. It's not popping out, right? Okay, it's doing something, it's moving around, but it's much more fun when you do it this way, and it hops right out of there. Woo! Okay, so let's see what else we got here. Okay, I think this is actually on your worksheet today, right? So the first one on your worksheet says a wire carries current to the right in a magnetic field directed out of the page. Okay, so sketch that on your page. Magnetic field out of the page you would represent with things coming up at you, right? So you could draw little dots to represent things coming up out of the page at you. Okay, wire carries current to the right. Okay, so predict for me which way the force goes in that first example. Who's got the right hand going? Anything? Down the page? Sounds good to me. Who's got down the page? Okay, excellent. Anybody questions on where down the page comes from? Okay, so you would have your page like this. Your fingers would be the current. You curl them in the magnetic field, which is coming out of the page. Which way is your thumb point? I hope I used my right hand. I did. That's getting it right. So that's down the page. Okay, no questions? Okay, try this one. This is the second one. Okay, so we get 70% for left, which sounds pretty good. We like that. Okay, so what should I do with my hand here? So if I hold my page like this, I've got my fingers directed into the page, and my magnetic field is directed down. So when I curl my fingers, I get the right direction. They're in the downward direction, and my thumb is pointing to the left. So that looks good for left. Any questions on where that came from? Get that? Okay. We can go over that later. Okay, how about this? So now we get three currents, three wires. The currents in these wires are identical, okay? In magnitude, that is. So these wires are carrying current from point A to point B. Now, wire 1 is taking the most direct route. Wire 2 is a strangely shaped wire with a 90-degree bend in it. And wire 3 kind of looks like a regular old wire that you may lay down on the tabletop, and it, follows that kind of path. So they all start at A and they end at B, and they have the same magnitude current. And what I want to know is which wire experiences more force in this case. Okay, so wire 1, wire 2, or wire 3. And you will notice there is a magnetic field. And so that is why we have any force at all, because there is a magnetic field. So we got more votes for wire 3 than anything else. And of course, our equation does have an L in it, doesn't it? And it's quite clear that 3 does have the longest length. Okay, so that would be certainly a good reason to choose 3 compared to 1 or 2. So let's forget 3 for a minute. Okay, let's just compare 1 and 2. They don't have the same length either, do they? Which one's longer? 2. So 2 is clearly longer than 1. So let's analyze the force that 1 feels compared to the force that 2 feels. Okay? Okay, so how do we do this? So we're working with the equation force is I, L, B, sine theta. The sine theta piece is important. There is a theta shown right here. Is this the theta that's in the equation? Well, let's see. The theta in the equation is the angle between the current direction and the field. So for wire 1, that is theta, isn't it? That is the same theta that's in our equation, right? The current direction is right along the wire from A to B. So there's our current direction. Our field direction is clearly to the right. So that is the theta we need in our equation. Okay, good. So we get whatever the current is times this length, how long that is, times B. B is the same for all wires, times sine of theta. Okay. Fine. So that's wire 1. Wire 2. Wire 2, you can look at the 2 separate pieces. Okay. So just worry about first this side of wire 2. And then we'll separately worry about this side of wire 2. Okay. When you do ILB sine theta on this side, what do you get for force? You get 0? Who agrees with that? In fact, there's no force. Just like there's no force on a charge that's going parallel to the magnetic field. Well, this is a whole bunch of charges moving parallel to the magnetic field. None of them feel any force. And so again, if you're worried about the ILB sine theta equation, well, the theta is 0 in this case. The current's this direction, the field's this direction, theta is 0. Sine of 0 is also 0. Okay, so absolutely right. You go no force at all on this side. You do get plenty of force on this side, on the other hand. Okay, and so in that case, you would get the current, the same current we used over here, so that factor is the same. This length, which is actually not the same as this length. In fact, this length is shorter than that length. Okay. B, well, it's the same B for wire 1 and wire 2. And for this side of wire 2, what do we use for theta? 90 degrees. Okay. So we get this length, and we get sine of 90. Whereas for wire 1, we get this length and sine of theta. Well, what is this length times sine of theta? You got a lovely right angle triangle here, right? So this length, sine theta, gets you the length of the opposite side. Okay. So our conclusion, comparing wire 1 to wire 2, is which one feels more force? They are, in fact, exactly the same. Okay. So if wire 1 and wire 2 feel exactly the same force, what might you think wire 3 feels? it's going to turn out to be the same as well. Now, let's try and make that a little more obvious. Okay, so I'm going to redraw wire 3. Okay, so I'm redrawing wire 3 like this, which looks a little funny, but bear with me. So we can add up all the forces on these sides which are parallel to the field, and we will get 0. So all the parts of the wire that run parallel to the field contribute nothing. There's no force at all on those. ILB sine theta, it's theta equals 0, sine theta equals 0. So we're only getting force from the perpendicular components, the parts of the wire that we've put perpendicular to the field. And here we've got a downward component, downward current, downward, 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 upward, 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 back to the same level. Okay, so we got a bunch of downward stuff and a bunch of upward stuff. What do you think is going to happen when we combine those two things? They will cancel out. And then we've got upward, 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 which happens to have exactly the same total length as this. And so this wire 3 feels exactly the same force as this side of wire 2. And of course, the other side of wire 2 didn't feel any force at all. Okay, so wire 1, wire 2, wire 3, and any other wire you want to run through this same field from A to B, carrying the same current, would all feel the same force. Okay? Does that mean that the magnetic force is conservative? It's certainly got a conservative, it's kind of got that conservative nature to it, right? It's like this path independence. We did the similar thing with the dipole and moving the charge around this thing. Yeah, right. So let me think about that. Ask me that again on Friday. I'll give you a better answer. I should know that off the top of my head, but I don't want to say the wrong thing. So ask me again. Okay, so how about this? So now we're going to take a loop in a magnetic field, and this is a uniform magnetic field. You can see that because you got all these x's that are equally spaced. Okay, so the x's represent magnetic field which runs in what direction? X's mean away from you, right, into the page. So we got magnetic field, of course, it probably says that up there too. So magnetic field is into the page, and there's just a beautiful rectangular loop carrying current around, and I want to know what direction is the net force on this loop. Okay? So give me the best answer you can to that question. Okay, so you can break this up into 4 sides, and you can analyze the force on each side. And what you should find is, in fact, the force on the left is exactly balanced by the force on the right, and the force on the bottom is exactly balanced by the force on the top. And so when you add them up, you in fact get 0 as your net force. And this is always true. You have a current carrying loop of any shape in a uniform magnetic field, and this word uniform is very important, in a uniform magnetic field, and you get no net force. Okay? And we could change the field direction. The field lines are actually cut off on this picture, and analyze it again, and we'd still get no net force in this particular case. How about this? Is there a net anything on the loop? So in this case, the currents are going this way, and let's pretend the field lines are running left to right. I've cut off the arrowheads cleverly. Do you get a net anything? What am I talking about? What might you get a net anything of? No net force. There's actually a net torque, and then you can do fun things like this. So here we have a loop in a magnetic field, and I'm going to run a current around the loop, and because we get a net torque on it, no net force but a net torque, it actually spins around. Okay? So this is a motor. This is how you make a motor. So we're going to talk about that starting off next on Friday. Okay?